Hello, my name is Alex Robb from the Hanson Research Group, and in this video abstract, I will be discussing our publication entitled Role of Metal Ion Linked Multilayer Thickness and Substrate Porosity in Surface Loading, Diffusion, and Solar Energy Conversion, which was published in the journal ACS Applied Materials and Interfaces. To begin, our group has pursued metal ion linked multilayers for some time now, and for a more in-depth discussion of this process, I would encourage you to watch our previous video summary in which we discuss our perspective article, in which we account our work in the area of metal ion linked assemblies. But in short, metal ion linked multilayers offer an easily prepared and modular architecture for controlling energy and electron transfer events on nanoparticle metal oxide films. However, unlike with planar electrodes, the mesoporous nature of these metal oxide films inherently limits both the thickness of the multilayer and subsequent diffusion through the pores. So thus, we sought to systematically investigate the role of TiO2 nanoparticle film porosity and metal ion linked multilayer thickness in surface loading, through-pore diffusion, and overall device performance. The TiO2 porosity was controlled in accordance with a previously published article, in which increasing the amount of time spent at the max ring sintering temperature, 500 degrees Celsius, increased the average pore diameter. Once films of different pore size were able to be produced, the molecular multilayer thickness was then controlled through assembling zinc-linked bridging molecules between the metal oxide and the RUP dye, thus producing TiO2 bridged films. Using attenuated total reflectance infrared absorption and UV-vis spectroscopy, we observed that at least two molecular layers could be formed on all films, but subsequent loading was dependent on the porosity of the TiO2. Rough estimates indicate that in a film with 34 nanometer average pore diameter, the maximum multilayer thickness is in the order of 4.5 to 6 nanometers, which decreases with decreasing pore size. These films were then incorporated as the photoanodes in dye-sensitized solar cells, with this cobalt bipyridine derivative being used as the redox mediator in order to add steric bulk. In agreement with the surface loading studies, electrochemical impedance spectroscopy measurements indicate that mediator diffusion is significantly hindered in films with thicker multilayers and less porous TiO2. Collectively, these results show that care must be taken to balance multilayer thickness, substrate porosity, and the size of the redox mediator when designing and maximizing the performance of new multilayer energy and electron management architectures. And thus, with that, I would like to thank you for listening to this brief video abstract, and if you're interested in further reading, feel free to click the link in the description to read the article and learn more. As well, if you're interested, feel free to follow our research group on Twitter and Instagram at HansonFSU. Thanks again.